live monitoring of macromolecules in solution under native, biologically relevant conditions. Capable of detecting particles at low concentrations with minimal buffer constraints in a matrix-free environment where no standards are required. An AUC is a specialized ultracentrifuge equipped with absorbance and interference detection systems. The inside chamber contains the rotor and the optic systems, including the lamp, reflector, lens, and photomultiplier tube. A centrifuge cell containing the sample is placed in the rotor for analysis. A variant of the centrifuge cell, a double sector cell, enables reference materials to be placed in a cavity alongside the sample, allowing the absorbance of the solvent to be corrected. The instrument spins the sample under vacuum at a set temperature and speed up to 60,000 RPM, measuring an optical density or a refractive index along the cell radius over time to provide insight into particle conformation, structure, stability, and interactions with other biomolecules. In AUC, centrifugal force is counteracted by buoyant and diffusion forces. The direction of sedimentation is opposite the center of rotation, as illustrated by this section of the centrifuge cell. Two types of experiments are typically performed using AUC: sedimentation velocity or sedimentation equilibrium. Sedimentation velocity is performed at high speed. The high speed depletes particles away from the center of the rotor and creates a pellet at the bottom of the cell. Each line on the graph represents a wavelength scan. As the protein sediments towards the bottom of the centrifugation cell, the wavelength flattens. The distribution movement over time is used to calculate the sedimentation coefficient, diffusion coefficient, effective mass of solute components, shape, and molecular weight of the particles under study. Sedimentation equilibrium is performed at lower speed, so it does not create a pellet at the bottom of the cell. Simultaneous sedimentation and diffusion forces produce a gradient across the centrifuge cell, and an equilibrium is reached when the opposing forces reach a balance. The data is plotted as sample absorbance versus radial distance from the center of the rotor, where the slope of the curve provides information on complex molecular weight. The distribution movement over time is used to calculate the molecular weight and homogeneity of the solution under study, as well as association constants and aggregation states.